Good afternoon, and I would like to thank the organizer, the EU PolarNet, the European Polar Board, and IceArc, to kindly invite me to give this short talk about the scenarios for Arctic change and global consequences in 10 minutes. These days we are playing dashboard. This is one we prepared for the COP21, and you will see that maybe a refined version of this first attempt. It's an ice-centric vision of what's going on in the Arctic, with a different form of ice, and as Sir David King introduced you to the subject with the sea ice, the ice sheets, the ice caps of covering Greenland, for instance, and northern Canada, and also the permafrost, the frozen land, which is another important. And it's extremely important to distinguish between these three forms of ice, because they have nothing to do with altogether, except they are related to a freezing point, so the cold temperature, but the origin of these ice are different, and the impact and effect on the global at the global scale is also very different. I'm not going to talk about all these what's on this graph. I will concentrate, because of the COP, on the climate effect. So this will be mostly in this sector of the of this graph. Another dashboard, if you wish, it's the Access, Arctic climate change and impact on economy and society. This is an EU project that we just concluded recently, funded by the European Commission, and dealing with the impact of climate change on different human activities like marine transportation, fisheries, resource extractions, and also in the scope of the governance, since the Arctic is governed in very different ways as the Antarctic is. So most of the result, some of the result I am going to show are coming from this recent project. IceArc is in some ways a continuation of Access. Just to put this in the context, you have seen this graph many times. This is the models, projections from the Ipcc, and showing different scenarios. The extreme scenarios with business as usual, the emission of carbon dioxide in particular, to a high rate, and more moderate scenario, so-called RCP 2.6, leading to two different situations as far as the global temperature is concerned. The upper part is 4 degrees or above. The lower part is the 2 degrees, which is what is the big deal of this conference these days. But you can see even on this graph that the Arctic is in any scenarios above the 2 degrees limit. And since everything is governed, as you imagine, by this freezing temperature, the freezing temperature in the Arctic is really a tipping point. And speaking about several degrees across the tipping points is triggering a lot of consequences. One consequences concern these mineral resources, hydrocarbons. We know that there are a lot of resources already. Some of them are exploited in the Yamal Peninsula on the land. There are others which are well known, like Stockman in the central Barents Sea. At the beginning of Access, we were planning to have some kind of direct actions with Stockman, but Stockman was closed because for economical reasons. But this gave you an idea of these resources, which are far significant and maybe of importance in on a planet where the growing population is going to increase by 3 billion more by the end of this century, as demographers are saying, it's interesting to see that most of these resources are located in regions where the sea ice tends to retreat. Same for shipping, short circuit by the pole for reaching Europe, linking Europe with Asia or North America. So there are different routes, in particular the Northern Sea route, number 1 on this graphic, north of Siberia, which is open quite a significant time every year, not all the year, but some in summer in particular. There are a lot to say about these opportunities, if we may say so, that I don't have time to comment, but maybe if you have questions about it, we will try to answer. But we are far from situations where these routes will be fully exploited, like Suez Canal or Panama Canal. But this is something we are considering mainly in the sense of exploiting Arctic resources. You know, if you want to use resources in the Arctic, you have to export these resources from the Arctic, and this is what's occurring at the moment in the Yamal Peninsula with some heavy exploitations. Back to the scenarios. This is the Ipcc scenarios in some extreme case, business as usual or a more moderate amount of carbon dioxide emission in the atmosphere. And you see that for each case, we have quite a large uncertainty on the response of the system. This is the extent of ice, by the way, in million square kilometers for sea ice during this period at the end of the summer in September. So this is the sea ice minimum in September. So it was more like 8 million square kilometers 100 years ago, and going down to almost zero at the end of the century, according to these prediction. But what's also appearing on that is we put some observation result on this graph, showing that we are on the lower limit of any prediction, any scenarios predicted by IPCC. Why is it so? And how reliable are the models, or how to deal with the observations? I want to stress your attention in a few minutes, since we don't have much time, on one point that Sir David King made about the sea ice volume. If the sea ice extent in the Arctic is retreating by half, from 16 million square kilometers to 8, like it was the case 30 years ago, and at the same time, if you reduce the ice thickness by half also, from more than 3 meters to less than 2 meters on average, it means that you are losing 75% of the ice mass or the ice volume. 50% extents, 50% thickness, 70% mass. And this is what we observe. So the ice volume, among all the parameters you can identify in sea ice, is the parameter which is changing the most rapidly and by a large extent. And what's important on this graph, this is a result of the biomass, Pan-Arctic Ice Ocean Modeling and Assimilation System. It's not a prediction. You see, it's not going over 2015, so it's just assimilating data and in a coherent way in a model to tell you what's the situation about sea ice volume. And what's important here, I want to stress your attention on two curves: the peak, the maximum in winter, and the minimum in summer, which evolve about the same rate. You see that the melting, which is the difference between the mean and the max, is about the same over the last 30 years. It has increased by 2,000 cubic kilometers because of the length of the summer. But look, In winter, the decrease in sea ice volume is as much as 10,000 cubic kilometers, 3 times more. So this is very important to identify, to attribute the cause for ice melting, which is not entirely, at least, dominated by the albedo effect in summer, but there is something else coming from the atmosphere or from the ocean which governs this evolution in sea ice. And I will tell you a few ideas that are still at work at the moment to try to understand what is the cause for these evolutions. So this is the lower curve. I don't want to spend too much time here, from which you could predict that ice in summer, not in winter, the ice will not disappear. It will come back in winter. Remember that. But in summer, obviously, it's going to end sometimes. According to these observations and to the model estimated with biomass, it will make an ocean free of ice few days, maybe, at the end of the summer in 2020. Not too long from now. The models, the Ipcc model, which are more broad scale and averaged, are predicting something at a later stage. I showed that on a graph already. The upper curve showing the 10,000 cubic kilometers decrease in winter, in the maximum in winter. We try to validate these by calculating how much ice you can form in winter with freezing temperature. And there is a very easy calculations to do. Once you have the air temperature above the ice, everywhere in the Arctic through the whole winters, you can calculate the number of freezing degrees days, from which you can deduce the amount of ice you can form. 2,000 freezing degrees days, you can form 1 meter of ice, roughly speaking. And we, using these simple calculations, we compared the biomass, the green curve, the biomass sea ice volume in winter with the calculations of ice volume coming from the freezing degrees days. At the beginning, you see a difference here, a significant difference, which is due to the fact the freezing degrees days are able to calculate only the new ice, the ice you form any particular winter. You ignore the ice which remain in the Arctic, which is not the case with biomass. But with time going, this multi-year ice, this perennial ice is disappearing, as we know, and both calculations are surprisingly pretty close, which indicates again the importance in winter conditions in the Arctic. The Arctic is not anymore a freezer working at minus 40 degrees on the average, not even minus 30 degrees, it's more like minus 20 degrees. It's still cold, you still form ice, but less than before. So it's not only the ice you melt in summer, it's the ice you don't form in winter, which really matters. This is also an indication of these freezing degrees days. Sorry about the colors. The red are the cold. So you see in early years, the cold is, the pole of the cold is north of Canada here, and it's not anymore, I mean, it's still colder here, but much less than before. We lost about 2,000 freezing degrees days over the last 30 years, which explain the reduction of sea ice by 1 meter. And 1 meter by 10 million square kilometers, that's the 10,000 cubic kilometers that are missing. It's coherent as far as rough numbers is going. My last slides are for showing that it's not only an average global temperature, it's not only number of freezing degrees days in winter over 200 days, for instance. It's also a day-to-day situation which is changing, as indicated for January 2010, when you have an indication of a warm Arctic. You see Greenland is 12 degrees above normal temperature. The same with Alaska and Chukotka here on the other side of Bering Strait. So the whole Arctic is warming. At the same time as the mid-latitude over North America and Europe, Eurasia, are really deep cold. I mean, it's minus 12 degrees below normal temperature. And we identify this problem with some kind of instability related to a weakening of the polar vortex. The jet stream, which is enclosing the cold air masses above the pole, is weaker than before. So there are a lot of instabilities at the periphery. As indicated on this graph, the jet stream is meandering a lot around the North Pole. And at the same time, you have these intrusions of cold air, which we call cold air outbreaks. That explain the cold temperature I showed on the graph before. And at the same time, they are compensated by warm air entering into the Arctic. So this is part of the phenomenon that may explain in part. The other part is this is the atmosphere. The other part is the ocean, and all the heat that the surface ocean has absorbed during the summer and that is released during the winter. Conclusion. I am not going to read all of that, only stress your attention on the winter effect, which is the central part in this paragraph here, with some kind of explanation about long-wave radiations and heat advected from lower latitudes to the Arctic and compensated by cold air being exported to mid-latitude. Also, an important part is this early breakup in the spring and late freeze up during the fall that we have been also recording. It's not only ice disappearing in the summer, it's the breakup in spring and the freeze up in the fall which are moving apart. So the opening the Arctic to a free ice period more and more. Something like of the order of a month or more. And that's my last transfer concerning the global consequences. The most important is this paragraph here, sections, stressing your attention on the strength of the polar vortex, which is weakening. In the Antarctic, it's just the opposite. The polar vortex around the Antarctic is pretty stable and sturdy, and the difference with the Arctic. And this effect has a large potential for releasing the methane, which is trapped under the permafrost, and also to disrupt the ocean conveyor belt by inundating the oceans with a lot of fresh ice coming from the fresh melting ice, bringing fresh water in the oceans and increasing the sea level by the same token. Finally, I think, like was said before, the canary in the coal mine, I think the Arctic has global consequences, which are very important because the climate change here is amplified and in some way anticipated for what's going to occur elsewhere. These 2 degrees time of limitations that we are all talking about, and I presented in my early graph, is just, I don't want to say it's a mythology, but we want to make sure that we are really keeping on track with this global temperature increase, and everything we can learn in the Arctic will help us in increasing the reliability of these models. Thank you very much. Yeah.